this is a serious moment for all of us, because once I say what I'm about to say,
oh gosh,
this is the point of no return, okay? You'll no longer be able to say, I'm not a rocket scientist. You'll be able to say, that's not rocket surgery. You know, you can still do that, but you won't be able to say, I'm not a rocket scientist. So this is the notion, right, is that here's this rocket. It's off, let's say it's in space, and there's no air in space, correct? Okay, so the question is, how do rockets propel themselves when there's nothing to push off of, right? Like airplane propellers can, like, they basically have like a screw on them and they move through the air like that, right? But in space, rocket engines can still work, and the answer is Newton's third law, okay? The rocket shoots molecules of exhaust gas this way, but for every action there's an equal and opposite reaction, and so if you push the mass times the velocity that way, a force times a certain amount of time is exerted on you. If you push the gas that way, you get pushed this way. And all jet engines, all rocket engines on Earth work this way. They don't push off the ground, they don't push off the air, they push off the fuel that is exiting their rear ends. Okay? There we have it. Yeah, that was a vivid image there, right? Okay. So in this case, we just recast this. This formula is the formula we use for rocket science. So you see how I was getting you to do rocket science before we even called it that?
Yep.
See how sly I am? Always weaving. Okay. So F is our engine thrust. T is the burn time, the time that we burn. And then M is our mass of fuel burn. And V is now our exhaust velocity. Same thing. Force times time is mass, change in velocity. Okay. So let's do an example problem. Let's suppose that a certain rocket engine burns fuel at a rate of 5.2 kilograms per second. Uh-oh, didn't talk about kilograms per second, right? Let's suppose that the exhaust velocity is 1,325 meters per second. These little, a liquid fuel rocket engine might do that. These little guys actually have an exhaust velocity. It's something like Mach 2. Honest to God, we used to test these things. That's safe. Is that safe? I don't know. Don't put your finger behind it when it's running. Yeah? Okay. So here's what you do. If they give you a fuel burn rate in kilograms per second, this clearly is our exhaust velocity. This is both the time and the mass. Let me just show you. So to solve this thing, I'm going to go force, and then the question here would be, what's the thrust of the engine, right? So I'm going to go force times 1 second equals 5.2 kilograms times 1325. And you see how I've done that? Doesn't that mean if it's 5.2 kilograms per second, doesn't it mean 5.2 in 1 second? So when they give you kilograms per second, just make time 1 and then just solve it, right? So we can do this. This is a lot of thrust. 5.2 times 1325. This is 6,890 newtons of thrust. Newtons. If this were an Estes rocket engine, it would be a X6890 engine or something like that. It would be some letter other than, they keep going. There's D, E, F, G, it would be like Q or something, I don't know. Right? And then this is actually the force, average force that they put in there. So a D12 averages 12 newtons, a C6 averages 6 newtons, kind of ish. Yeah? Yeah? You guys want to try this?
oh yeah.
Yeah? Holy example number 1, skipping example number 2, because I'm going to have you try that problem. A certain rocket engine burns that much fuel per second, so that's that kilograms in 1 second, correct? Okay. The exhaust gas velocity is 725 meters per second. And that would be typical, a typical exhaust gas velocity for one of these little model rocket engines. This would not be, though, a legal one you could buy at Michael's Arts and Crafts store. I go to Michael's like once a year. 25 point. Do you get 25.5? Is that what it says?
Yeah.
Yeah. You have 3 sig figs. That's right. Yeah. Yeah, give me some units there for force. Let's say 25.5. I can't read it. That's right. That's right. You're going to increase your font size. That's like 36 point font. Try Boogala point font. Boogala. Yeah. Yep. That's right. That's right. Bradley Barrow, Bradley Barrow, Bradley Barrow. Quit surfing internet. Ah, that's right. Hey. Give me some units for force there. That's right. Does that say newtons? I love that. Yes. Yes. Yep. Bradley, I need you to participate in class. Tanner? But don't make me go over there and turn off the monitor. I'll do it. Don't make me do it. Why doesn't Brandon need his whiteboard? Is that 25.5, Nathan? Nathan. Nathan Love, Nathan Love. 25.5, is that a decimal point? I love that. Yeah. It's newtons, because you divide it by seconds. It's just 1 second, so. Are you ready for the next one? A Saturn V rocket. I'm very proud of this one. Saturn V rocket is this guy, though. We're talking about the first stage engines, the largest ones. Generated 33.82 mega newtons of thrust. That's 33.82 million newtons, or 33.82 times 10 to the 6 newtons. Wow. And then the exhaust velocity is highly accurate too. Exactly. Actually, I know what the mass burn rate was, so I just kind of did the. So you're solving for m. What's the trick here? Do you just make time 1? Yeah, make the time 1. So this is 1. Force is 33.82. And you're solving, when it says solve for mass burn rate, make time 1 second, solve for m. There you go. That's a lot of kilograms. Yeah. Yep. That is 15. I almost put your eye out. Oh! See what you did? You have a handicap.